let's talk about one-dimensional consolidation laboratory testing. So our goal in this test is to measure the volume change of soil under one-dimensional vertical loading. So basically we want to impose vertical loading on the soil and measure how much it settles. It's obvious why we would want to do that, because that's exactly the problem we want to answer if we build a structure. How much is the structure going to settle? Well, first, let's take a look at what does one-dimensional mean. What we mean by that is that the strain tensor is constrained so that you have a vertical strain component that is non-zero, and all of the other components are zero. So we have to prevent any horizontal strain from happening, and there can also be no shear strain in any direction, only vertical strain. So under that condition, the volumetric strain is equal to the trace of the strain tensor. So basically you add up all the components on the diagonal. So you can see here that the volumetric strain is equal to the vertical strain for one-dimensional loading. Now in general that's not true, right? Volumetric strain is not equal to vertical strain if there's any other kind of horizontal strain happening. So like in a triaxial test, we strain the soil vertically, but it bulges horizontally. So in that case, you can't compute the volumetric strain based on the vertical strain. You have to measure it by the amount of water that's flowing in or out of the specimen generally. Okay, for consolidation testing, it's a special case. We're constraining the strain to only be vertical, so vertical and volumetric happen to be the same. So how do we achieve this loading condition in the lab? How do we get this vertical strain with no horizontal strain? Well, that's when we use a one-dimensional consolidometer. So these images show two different types of one-dimensional consolidometers. This is figure 8.3 from the Holtz, Kovacs, and Sheehan textbook. The first kind here is a floating ring consolidometer, and that's where there's both of these drawings are cross-sections through what is a circular cross-section in plan view, so a cylindrical soil specimen. And you have this really stiff ring that goes all the way around the soil specimen in that direction. And so basically, even though the metal does have a finite Young's modulus, when you load it, it will expand slightly. The amount of expansion in that hoop direction is so small that we can basically consider it to be one-dimensional loading. We've prevented horizontal strain. We also don't want to have friction between the soil and the ring. If there's any friction, then you get shear stresses along those interfaces. And again, we don't want to have any shear stresses, right? We can't have any of those, so we want this to be frictionless. So the metal is very smooth. And there may be some friction, but the size of the soil specimen relative, basically the diameter relative to its height is pretty big. And that way, all of the friction that happens over here and over here doesn't really affect the overall response of the soil very much. So the floating ring is not supported by anything. It's held in place because there's horizontal pressure between the soil and the ring. And then there's a porous stone on the bottom and a porous stone on the top that allow free drainage, and then a loading plate up here. And then you can impose the load vertically on that loading plate, and the soil will settle. Notice also that there's a water table here. We try and keep the soil saturated. Usually consolidation tests are performed on saturated soil. We want them to stay saturated, so we make sure that there's always water in that little reservoir. All right, and then there's the fixed ring consolidometer. And in this kind of consolidometer, the ring is resting on the bottom of the consolidometer. It's not floating. It's not held in place by horizontal pressure. So the fixed ring is better suited for weaker soils. If you have a soil that's not very strong, the weight of the ring might actually cause it to fall down. This one is supported on the bottom. It's actually much more common, I think, to use a fixed ring consolidometer. But the idea is the same. You've got this water table here. There's a porous stone on the bottom, and you have to provide a drainage port, right? We want this water to drain out of the specimen, so there is a drainage port at the bottom of the consolidometer that allows that to happen. The porous stone's connected to it. So what we do, and if you take the 128L class, you'll do a test using this kind of fixed ring consolidometer. So then the test sequence, we impose a vertical load, so we'll put some vertical force on this loading plate up there. And then we measure settlement versus time. So we always have an LVDT attached to the top to measure, or a dial gauge to measure settlement versus time. And then after consolidation for a particular load stage has essentially completed, we apply the next load stage. So usually we do 9 or 10 load stages for a test. Some of them involve unloading, where we're removing force, masses from the top. Some involve loading. And so we repeat that, 9 or 10 times. Maybe 20, it all varies. And then when we're done, we post-process the results to try and get some material properties that we can use to quantify the consolidation behavior of the soil. So let's talk, I don't know why it's scrolling so fast. Here we go. Let's talk about some of the post-processing that we do. So what we do is we've measured the specimen height, and then we measure the settlement versus time, so we know the height at the beginning and end of a load stage. Well, that allows us to compute the vertical strain that occurred during that load stage, and then simply it's the change in height divided by the initial height. And then we can compute the void ratio, right? So we already know from previous derivations that vertical strain, volumetric strain is equal to minus delta E over 1 plus E naught, where delta E is the change in void ratio. 1 plus E naught E naught is the void ratio at the beginning of the load stage. Recall there's a negative sign here because for compression, delta E is negative. The void ratio is decreasing. And for compression, the volumetric strain is positive. So we have that negative sign. So if we substitute in here, delta E is just equal to EF minus E naught. We can put that here. And that allows us to solve for an equation for the void ratio at the end of the load stage. It's just equal to E naught minus epsilon V times 1 plus E naught. And then we plot the final void ratio versus the final vertical effective stress, where sigma V prime is the vertical effective stress at the end of the load stage. So you have to keep track of how much mass you're putting on. So here's an example calculation. And I wanted to illustrate something that's often confusing for students in this example calculation, and it's the reference state for computing strain. But first, let me just describe what's happening in this table. So up here, we have two cells that give us the initial void ratio and the initial height of the specimen. I should have units here. This is millimeters. And these values are at the very beginning of the test before we apply any load, right? So these ones are at very beginning. Okay, and it's common to put these in these cells at the top, and then they get called from functions in the table below. All right, then what we have here is load stage, and in this case, I'm only doing 4. You can increase it further if you want. Usually we'll do more than 4 load stages. I'm just kind of showing how to do the calculations. Then we have this column that is sigma V naught prime. Maybe, let me put units on this. This might be, KPA. And then this one also KPA. And one thing you'll notice that's always super confusing is that there's a question mark here at the beginning of load stage 1. The issue with this is that when we pull a specimen out of the ground, let's say we have a tube sample, we've pushed a tube in the ground, we pulled it out of the ground, we have this little ring of soil ready to go. The vertical total stress is basically 0, right? Because the specimen's so thin, the self-weight of the soil doesn't really contribute very much. But the problem is that we don't know the pore pressure. We can't assume that the pore pressure is 0. A lot of students assume the pore pressure is 0, therefore the effective stress is 0. The thing is, when you push the tube in the ground, you're pulling the soil out, and there's a big change in total stress. It goes from being whatever was in the ground in situ to being 0. Well, that change in total stress is actually taken up by negative pore pressure. So there's negative pore water pressure holding the soil together at the very beginning. We don't measure that. We don't know how to measure that negative pore pressure. So always put a question mark here in this cell. Don't put a 0. We we never even use sigma v naught prime in the end, so it doesn't matter a whole lot, but just keep that in mind. And then sigma v f prime would be at the end of load stage 1. We know that we've put some load on, so now there's a finite amount of total stress, and we've added water to that chamber and allowed the soil to soak up that water, so we know the pore pressure now, right? The pore pressure in the specimen will come into equilibrium with the little reservoir that we have. So we do know the effective stress at the end. Then what we can do with these effective stresses is simply move this cell down there, so that for stage 2, the initial effective stress is equal to the final effective stress for stage 1, and usually we double the stress with each load stage. So here we go from 10 to 20, the 20 goes down there, here we go from 20 to 40, and the 40 goes down there, and load stage 4 goes from 40 to 80 kPa. Alright, then using our dial gauge or our LVDT, we know the initial height, right? This one is simply equal to this one. And then we measure the change in height, and we'll get some final height. So the 0.019 would be the result of a vertical load cell measure, or vertical displacement measurement. Then similarly, that one goes there, then we measure again, this one goes there, we measure again, and we work our way through. Alright, so that's all the input, right? These cells right here that I'm highlighting, those are input parameters. The rest is all calculated, so you don't need to put in any more data after that. Delta H is simply equal to H naught minus HF, right? That's the change in height, and it's compressive, so a vertical compressive displacement is positive, which is why I've got this here. Okay, now here's the part that gets a little confusing. Students often ask me, do we use the incremental strain, which is the change in height divided by the initial height for each stage, or do we use some sort of cumulative strain, which is the change in height from the very initial condition divided by the very initial height? And the answer is that you can use either one, and it's more common to use the cumulative strain. You'll get the same final void ratio either way, which is what we're trying to get here. So I've walked you through it. I probably have too many significant figures here, but I would reduce that if it was an assignment. So forgive me for leaving it at like, what, 9 sig figs here. But anyway, this value, epsilon v for column G, it's defined by this equation down here. So G5 is equal to F5 over D5. I'm simply taking the change in height divided by the initial height of the specimen for that load stage. If we go to G6, this cell, it's equal to the change in height divided by the initial height for that load stage. So that's the amount of vertical strain that happened during that load stage. Alright, the cumulative one is a little different, right? So there's 0.05, these two are both the same, but then they start getting different when you come down here. So let's take a look at the equation for the cumulative one. It's right here. So now I'm using the very initial height, $B, $2. So the $sign basically means that we're always referencing this cell, B2, even as we drag and drop. So, you know, this one down here is still referencing B2. And so what we're doing here is using the change in height relative to the initial height. So B2 minus E5, right? $B, $2, so always 0.02, minus the final height of the specimen at the end of each load stage. That's like the cumulative amount of settlement that's happened since the very beginning. And then we divide by the very initial height at the beginning. So it's just a point of reference issue. And usually we pick the point of reference to be at the very beginning of load stage 1 rather than updating it for each load stage. But I did want to show that you get the same final void ratio either way. Alright, now E naught is the initial void ratio. So at the beginning of stage 1, it's equal to the initial void ratio at the beginning of the stage. So this one would be like equals B1. Then EF is, you can compute it using the incremental equation or the cumulative equation. So using the incremental equation, we have here, this is J5, right? So J5 is equal to I5 minus G5 times 1 plus I5. So I5 is E naught. And then we had a minus G5, which is the incremental strain times 1 plus E naught. So the equation we're using is this equation. But the strain we're using is incremental, not cumulative. And we get this column for final void ratio. Okay, then there's also an equation we can use based on cumulative strain. And that equation is shown right here. It's now $B$1 is the void ratio at the very beginning of the test. Okay, we're not using the void ratio at the beginning of each load stage. We're using the very initial void ratio at the beginning of the test. And then we're using the cumulative strain instead of the incremental strain in this equation. And you'll see that these values are exactly the same. So whether you use the initial condition as a reference point for computing strains, or you update your point of reference for computing strain as you go to be at the beginning of each load stage, doesn't matter. You get the same final void ratio. All right, then what we'll do is plot void ratio versus sigma v prime. And usually, let me put a KPA in here. Usually what we'll do is put this on a log scale. I'll talk about that in just a second. It's also common to plot cumulative strain versus sigma v prime on a log scale as well. So these two curves basically look the same. It's just that the vertical axis is means something different, right? This is cumulative volumetric strain, this is void ratio, but they are linearly related to each other. All right, now let's look at what real data looks like. This was an example problem. Now I'm going on to look at some real data from figure 8.4 in your textbook. And this one, I guess they're putting void ratio on the right and cumulative vertical strain on the left, so it's kind of switched from what I showed before. But this is from San Francisco Bay mud, very common, kind of famous clay in the Bay Area. And what you see is that the curve has this sort of shape where it kind of curves down. So as you continue increasing stress, the amount of strain you're accumulating becomes smaller and smaller because the soil is getting denser and denser. So here's the loading. Then they reached a vertical effective stress of 800 kPa and then did some unloading. And you get this kind of unloading curve. And then here's the same thing, but in void ratio space, instead of vertical strain space. And they look kind of the same. And I'll come back and talk about this ACE of V and what that means in just a second. All right, now, the reason why we use a log scale a lot of the time in geotechnical engineering is that it tends to make things linear. And that happens with consolidation testing. So when we do this transformation of the x-axis and just plot it on a log scale instead of a linear scale, we see now that this is a pretty much a straight line. Maybe not totally a straight line. We can model it as a straight line. And similarly, this one is also kind of a straight line, right? So we could approximate that as a linear fit, whereas if we do it in regular, linear space, not log space, there's no way to approximate that curve as a straight line. So, and similarly in void ratio versus effective consolidation stress space, you get this linear fit right here. Now, I'll talk about this more in the next lecture, but you might be wondering, why does the curve have kind of a gentle slope and then all of a sudden it gets really steep right here? Well, it turns out that this point right around here, that I'm highlighting, that's the maximum pressure that the soil's experienced in the past. So before you get back up to that pressure, the soil doesn't settle very much. Once you exceed the maximum past pressure, it starts settling a lot. We'll go through that later. But that's why the curve looks like this. And then when you do an unload stage, it's like the soil doesn't rebound all the way back to where it was. You permanently squeeze water out, and when you remove load, it rebounds a little bit, but not all the way to where it was before. So let's talk about some definitions. First of all, there's A sub V, that's the coefficient of compressibility, and that's defined as minus dE over d sigma V prime. So let's come back up to this one. Notice that we're plotting, here's void ratio versus effective consolidation stress. So we can get A sub V from this plot It is simply the tangent slope of this line at any point. So one thing you'll notice is that A sub v varies, right? There's going to be a much different A sub v over there than there is right here. So A sub v is not a material constant. It depends on effective consolidation stress. And it's also different if we're on this part of the curve that's, loading beyond the maximum past pressure, or if we're unloading. A sub v is much smaller if we're unloading than if we're loading along this line. Okay, and then there's also M sub v. Whereas A sub v is formulated in terms of void ratio, M sub v is formulated in terms of cumulative volumetric strain. So if we come back up again, this curve now is what we want to look at. This is cumulative volumetric strain versus effective consolidation stress. And it's not drawn in here, but I can draw it. So here, I'll draw it right here. That slope right there, that would be M sub v to 1. Right, so A sub v and M sub v are related to each other by our definition of strain. It turns out that M sub v is just equal to A sub v over 1 plus E naught, and that's the coefficient of volume compressibility. All right, then the next lesson will really further define these last three concepts. I just want to introduce them here. C sub c is the virgin compression index, and it's defined as minus dE over d log sigma v prime. For the loading condition where the initial effective stress is equal to the maximum past pressure that the soil's ever experienced. So we're loading the soil further into territory where it's never been before. It's never experienced loads this big. So if we go up here, here's the slope of the C sub c line. This is the laboratory virgin compression curve. This would be reloading back up to sigma p prime, and then virgin compression is there. So that the slope of the virgin compression part is C sub c. All right, C sub r has the same equation definition as C sub c. We're just looking at a different part of the curve. So this is now where the final effective stress is less than sigma p prime. And so that would be the case like right here, right? We've come to this high pressure out here, 800 kPa, now we're unloading. So sigma vf prime is only 200 kPa, but sigma p prime is 800. So it's also not drawn, but I will add it. That slope right there is C sub r. And C sub r is less than C sub c. Okay, and then sigma p prime is our maximum past pressure. It's the biggest pressure that the soil's ever experienced in the